this video, we're going to go over a new type of number. So just to start an introduction, we're going to look at this quadratic graph right here. And I want you to think for a second, what are the possible solutions to each of these equations? We've got x squared equals 4, x squared equals 9, x squared equals 0, and x squared equals -1. And maybe in your head you have an idea about what the solution is, whether you solve this algebraically or just using some of your mathematical knowledge. But also take a second to look at the graph over here and see if you can find where these solutions might lie on the graph. So starting with x squared equals 4, I know that if I wanted to solve this equation, I would start by taking the square root of both sides. Oops, that's the highlighter. I would take the square root of both sides of the equation in order to cancel out that exponent, and I would get x equals plus or minus 2. Remember, when we take the square root, we have to consider both the positive and the negative. But where might that show up on this graph? So looking at the graph we see, we've got this quadratic equation right here. This is the parabola, and that is the parent function. So this equation right here in red, that represents y equals x squared. So for all four of these equations, x squared, that's the left side of the equation. So the x squared is represented by the red parabola. But then each x squared is equal to a different number. So for example, the first one we just did was equal to 4. Well, on this graph here, I actually see a line at y equals 4. So how could I use the red graph and the blue line to find the solutions that we found when we did this algebraically? Well, if I look at where the y equals x squared parabola is equal to the y equals 4 line, that would be where they intersect each other. So that would be at these 2 points right here. And if I look at where those points lie on the x-axis, that would be at x equals -2 and x equals +2. So we can see these answers, these solutions, both algebraically and also on the graph. So for example, for x squared equals 9, well, here's the line y equals 9. And if I look for the intersections, we've got x equals -3 and x equals 3. So the solutions here could be x equals plus or minus 3. How about for x equals 0? If I were to solve this algebraically and I took the square root of both sides, I could get x equals plus or minus 0, but positive 0, negative 0, really that's all just 0. And if you look on this graph, very faintly you can see a purple line down here, and that line is at y equals 0. And notice that that line only intersects our parabola in one place, because there's only one solution, which is y equals 0. But now we've got our very last one, x squared equals -1. And the line y equals -1 is this line right here. But I'm running into a problem on the graph, because this line doesn't intersect the parabola. So where are my solutions? Let's try to solve it algebraically. Take the square root of both sides, and we're running into another problem because we can't take the square root of a negative. This always gave us an error. Well, that's until today, because today we are going to learn what types of solutions an equation might have if we are taking the square root of a negative. So for the first 3 examples that we just looked at, those all had solutions that were considered real numbers. So real numbers, these are the numbers you're used to. You've done a lot of math with the real number line. They're just normal numbers. But now we have this new number because we have an issue over here, which is that when x squared equals -1, x equals the square root of -1, and this is not a real solution, but it is still a solution. We have now a new kind of number, and that number is called an imaginary number. And I know that it sounds crazy to talk about imaginary numbers, but they serve a big purpose in math. So we're going to learn about how we find these imaginary solutions, specifically with quadratics right now. On this picture of this graph right here, we have the imaginary number, the square root of -1, drawn on this graph because it doesn't fit on a normal number line because that's where our real numbers lie. So we need a different number line, the imaginary number line, to represent these numbers. So let's draw a few other imaginary numbers on this number line, starting with 3 times the square root of -1. So I see right there already the square root of -1 is graph for us. But if I want to do 3 times that, you can almost think about transformations. That would be like a stretch. It's going to stretch vertically by 3. So that would look like 1, 2, 3. There is the imaginary number 3 times the square root of -1. Let's try the next one. Negative square root of -1. Now in this problem, we have the negative in front of the imaginary number, the square root of -1. So now that's going to reflect us below the number line, and that's going to be right here. We're just going down 1 because it's the square root of -1, but it's been reflected, negative square root of -1. One more, we're going to do -5 times the square root of -1. So first I see that negative out front, which tells me I'm going down. And then there's a 5, so I'm going to go down 5. 1, 2, 3, 4, 5. Draw my arrow, and that's how I would represent -5 square root -1 on the imaginary number line. So we're learning about this new number. We've seen it on its number line, but what is an imaginary number? Oops. So imaginary number is a number which, when multiplied by itself, it gives a negative result. Up until now, we couldn't do that. There was no number that when you squared it, you got a negative answer. But now we have that with imaginary numbers. So, for example, the square root of -1, that's an imaginary number because when I multiply the square root of -1 times the square root of -1, I get -1. I get a negative answer. And so, in order to kind of simplify this down, because the square root of -1 is a lot to write every single time, mathematicians decided to invent the symbol I. I mean, did they invent it? I don't know. It's just the first letter of the word imaginary. But I is how we're going to simplify the imaginary number square root of -1. So anytime you see a square root of -1, you can simplify that to I. So where earlier we would have gotten the solution plus or minus square root of -1, now we see that the x squared equals -1. Really, our solution is I and -I. So continuing with our notes, these are what we've already gone over together. Just to recap though, an imaginary number is a number which, when multiplied by itself, gives a negative result. And the simplest imaginary number, I, is the square root of -1. So now how can we use I to simplify other imaginary numbers? For example, here I have the square root of -64. So that's a little bit larger than just the square root of -1. And to do this problem, I find that it's helpful to kind of break apart the pieces that we know. So I have a negative and I have a 64. And mathematically, we know that because they're both under the radical and they're being multiplied together, I can break this up into the square root of -1 times the square root of 64. Mathematically, that's still the same as what we started with. And the reason that this helps is because now I know what these two pieces are when they're separated. What we've just learned today is that the square root of -1 is I. So the square root of -1, that's I. But what we know from our prior knowledge is that the square root of just 64 is 8. So the square root of -64 is actually equal to the imaginary number 8i. And we can plot that on our graph over here. 8i would be, starting at 0, we go up, 8i. The next one, I've got negative square root of -100. Before I deal with the square root out front, I'm just going to look at, the negative out front, I'm just going to look at the square root. Square root of -100. Again, I can break this up into pieces that I know, because I know the square root of -1, and I know the square root of 100. That would be equal to 10 is the square root of 100, and then I is the square root of -1. Now, that's still in parentheses. I'm going to bring over that negative from before, and really what we get is -10i. So I'm going to go ahead and plot this on my graph over here. Go down to -10i. And finally, number 3. So in number 3, I can, again, break this up into the pieces that I know. That's the square root of -1 times the square root of 10. Now, I know the square root of -1 is I, but the square root of -10, well, 10 is not a perfect square. So we need to, one, look, can we simplify this radical? So are there any perfect squares that 10 is divisible by? But for 10, there aren't any. So that's one that we cannot simplify. It would stay the square root of 10. Now, that's a great answer when I'm simplifying imaginary numbers, but that doesn't quite help me for the graph. So in order to graph this, we could estimate that this is approximately 3.16i, just by taking the square root of 10 and rounding it. And then I can plot that number on my graph. That would be about right here. Now, with imaginary numbers, there's also imaginary numbers to powers. So sometimes we have to simplify radicals to find the imaginary numbers, but sometimes we have I raised to a power or an exponent. And so we're going to take a second to look at some of the first few powers of I. I to the first power. Well, that's just I. And what do we know that I is equal to? I equals the square root of -1. And of course, I to the power of 1, we could also just rewrite that as I. So all three of these things, those are equal or equivalent. Now, I squared. Well, I squared would just be the square root of -1 squared, because I is the square root of -1. Well, mathematically, we know that when you take the square root and then you square that, those two operations are inverses, so they cancel, and I'd be left with -1. So I squared actually reduces to -1. Now, how about I cubed? Well, I cubed, if we think back to exponent rules, that could be I to the first power times I squared, which I know I to the first power is just I, and I squared is -1, so this equals -I. And last, I to the fourth, that would be like I to the first times I cubed. Okay, so that's I times negative I, or negative I squared. But now we did just learn that I squared is negative 1, so that would be negative 1, which is positive 1. So really, these first four powers, I to the first equals I squared equals negative 1, I cubed equals negative I, and I to the fourth equals positive 1. Take a second, use the same ideas to try to fill in I to the fifth, I to the sixth, I to the seventh, and I to the eighth. So as you're going through this, I to the fifth, that would be like I to the fourth times another I. So that would be 1 times I, which is just I. And I to the sixth would be I to the fifth times another I. So that would be I from I to the fifth times I, which is I squared. But what we just learned is that I squared really simplifies to negative 1. I to the seventh, that would be like I to the sixth times another I. So that would be negative 1 times I, which is negative I. And then I to the eighth, that would be I to the seventh times another I. So that would be negative I times I, which would be negative I squared, which would be negative 1, which is positive 1. And do you notice any type of pattern here? I to the fifth equals I to the sixth equals negative 1, I to the seventh equals negative I, and I to the eighth equals 1. This is what we call the powers of I. So this pattern repeats forever and ever and ever. Every I to any power can always be reduced to an I, a negative 1, a negative I, or a positive 1. Now this pattern, the way that it works, you're going to have to remember kind of that pattern and how you can use it. And there's some ways that I like to remember this pattern. So starting with these first four, we've got the pattern is, the pattern is I, negative 1, negative I, 1. And the way that I like to remember this is I always think, who won? Who won? Who do you think won? Well, in my ideal world, I won. So the pattern goes, I won, and negatives go in between. Okay, so in order to remember the patterns of I, we think who won? Well, of course, I won. It goes I won, negatives in between. I won, negatives in between. Now that's great. Now we know the pattern, but how do I take any power of I and reduce it down to one of these four options in the pattern? And it's actually pretty easy. All you have to do, for example, if I want to do I to the 41st power, all I have to do is figure out where 41 would lie in this pattern of 4. And to figure that out, I can just take that power and divide it by 4. So I'm going to do 41 divided by 4, and I get 10.25. And I actually don't care about the 10 at all. All I care about is this 0.25, the remainder. And that remainder tells me where in this pattern I lie. Now, we're talking about winning. Well, if you're winning something, the best thing to win, of course, is money. So to help you figure out, well, what part of the pattern does this number lie, we can think about money. To get to $1 using quarters, you have 1/4 is 25 cents, 2/4 is 50 cents, 3/4 is 75 cents, and 4/4 is $1 full. So looking at your remainder, you can figure out where in this pattern that value lies, and that will tell you what that I to that power reduces to. So for example, I to the 41st power, that reduces to just I.